Okay, so question 12 here to pick up part 3 of homework 8-5. Much like the question we saw in class in the notes there, but if you do need a refresher on this, I'll go through this as well. All right, so stand by the side of the road, a car approaches you at a constant speed, sounding its horn. You hear a frequency of 80 hertz. As the car goes by, it drops down to 60 hertz. What is the speed of the car? Assume that the speed of sound in air is 343 meters per second. Right, so I've got some information to work with. The key here is neither of those frequencies is the actual frequency of the car. Right, this frequency is the frequency we perceive as the car is approaching us. Right, so as it's moving towards us, and then this frequency here is the frequency we perceive as it's moving away from us. So the key of this question becomes setting up both of those expressions using the Doppler effect. Right, so the frequency that we perceive as the car moves towards us would be calculated by taking the original frequency, right, times because it's the source moving, the velocity in air divided by the velocity, and when it's moving towards us, we're going to be subtracting the velocity of the source on bottom. Right, so I've got this set up. So if I look at the information I know, well, I know this is 80 hertz. I don't know the original frequency, right? That's what we're looking for the speed of sound. So never mind, we're looking for the speed of the car. So I don't need the frequency, but I don't have the frequency. I know the speed of sound in air is 343, so I know that on bottom as well. So obviously if I just look at one of these expressions, I get stuck because, hey, I've got two variables, and obviously you guys know at this point in your academic careers that we have two variables. We should probably set up another equation. So I'm going to set up my equation for as the frequency is moving away. Right? The frequency as it moves away would be basically the same setup, except this time we're adding in the denominator because the car is moving away from us, so the source is moving away. We know that this frequency is 60 hertz. In the original frequency I don't know, but I do know the following measurements here. So as soon as I get this all set up, it just becomes a system of equations. Yes, it can be a little bit tricky to solve this system of equations, but if you take your time, right, it's just following the algebra at this stage. So probably what I would do from here is go ahead and solve both of these for frequency. Right, so if I solve each of these functions to get frequency by itself, I'm just going to multiply by the inverse of this side. So it's going to be 60 times 343 plus the velocity of the source over 343. Right, I'm just multiplying by the reciprocal over here. And then on the left-hand side as well, just multiplying by the reciprocal of this. So my frequency would be 80 times 343 minus the velocity of the source divided by 343. Since it is the same frequency, right, the car horn did not change. We just perceived a different frequency. But since those frequencies are the same, then I'm really just going to set these two equations equal to each other. Right? And so as I do that, if I look at both sides, well, both sides I have a 343 on bottom. So then I just have 80 times 343 minus the velocity of the source equals 60 times 343 plus the velocity of the source. And from here I'll leave it to you to do the rest of this algebra here, right? But when you solve for the velocity, you should end up getting about 49 meters per second, and I think it actually may be exactly 49 meters per second, right, as we solve this equation. So anyway, make sure you're comfortable setting up these types of problems. Again, hopefully not too bad as long as you're comfortable setting up that system and then solving using some algebra. Okay, so question 13, last question here. Not a terribly difficult algebraic question to solve. The concepts here can be a little bit tricky though. So before we get into the mathematics, I want to make sure we are comfortable just kind of setting up and establishing this, right? So you've got a carousel that's rotating around in a circle, right? And on each end of a diameter of that carousel, you have a 600 hertz siren. So you have this siren that's making noise, right? So the carousel's spinning around, spinning around. You've got that siren on each end of the diameter there that is making a certain frequency, right? So they ask us, what is the longest wavelength that will reach a stationary observer? So let's suppose we have a stationary observer down here just watching this carousel, right? They're asking for what's the longest wavelength that will reach that listener's ears. Well, the key concept here is the frequency is going to change because as the object rotates, the velocity changes with respect to the observer, right? So what I mean by that, and obviously I'm just going to focus on one of these sound sources for starters, but at this location right here, the sound source would be coming completely directly towards, right, at least at that instant time, it's going to be coming directly towards the observer. An instant after that, the velocity is now going to be going partially towards, partially away. And then later, right, it's going to continue to go horizontal and then back in the other direction. At this location here, that frequency is going to be going completely, right, directly away from the observer, right? So the key becomes really focusing on those two side points, right? And again, I'm going to do this one at a time here. So if I look at this side of it as the frequency is approaching, right, as the sound source is approaching the observer, the frequency would go higher because the velocity is coming towards the observer, right? So we know that that would be, if I was using the Doppler effect, something of this nature right here, right? So that would mean my frequency is again going to be getting higher. So the question becomes, do I want a higher or a lower frequency so I can find the longest wavelength? Well, the longest wavelength is going to be associated with the lowest frequency, right? The longest wavelength, the highest, the biggest wavelength, right? If I think about my velocity equals frequency times lambda, the smaller the frequency, the bigger the wavelength, right? So I actually don't want this situation. Instead, I want to know the situation in which the sound source is moving directly away from us, right? So as the observer down here, if the sound source moves directly away, then we know that the frequency is going to be getting smaller, and therefore the wavelength is going to be getting bigger. So this is our goal. This is the relationship we want to start with, right? I want to start by finding that perceived frequency as the sound source is moving away from me. So let's see what information we know then. Well, again, I'm looking for the new frequency. I know that it makes 600 hertz, right? That's the sound source's frequency. And then I know that the speed of sound they're giving me is 350. So the question is, what's the velocity of the source, right? What's the velocity that we're going to be adding on bottom here? Well, the velocity of the source ties in with some of our good old angular motion, right? So they tell us the angular velocity in the question, angular velocity, which is my omega, is 0.800 radians per second. So if I want to use that to find my linear velocity, I'm just going to use the linear velocity equals the radius times the angular velocity. And since I know that the diameter is, that the radius is 5, right, I'm just going to take 5 times that 0.8, and I'm going to multiply that, and I'm going to get that this is 4, right? So my linear velocity is 4 meters per second, and so that's what I'm going to plug in for my new frequency, right? So my new frequency is going to be based off of this. So obviously it's not going to change by a ton, but it is going to drop a little bit since I'm dividing 350 by 354, right? So in fact, when I calculate this, this ends up being about 593.2 hertz. So again, that is the lowest frequency. That is the lowest possible frequency the observer will hear. Right? At the other location, he would hear something higher. At this location here, you actually hear the 600 hertz frequency, right? Because the velocity is not moving away or towards the observer. Right? So you should be pretty comfortable with that full spectrum of different frequencies that the observer will be hearing. But anyway. So I've got my frequency. It did ask, though, if I read the question, for the wavelength, right? So now I'm going to go back to just my velocity equals frequency times lambda. I know the velocity of the sound is 350, right? That's the velocity in air. I know that the new frequency I'm hearing is 593.2, so I can find my perceived wavelength, right? The longest wavelength from there. So the longest wavelength would be about 0.59 meters, right? So there's my longest wavelength that the observer will hear. Like I said, a good question. Make sure you're comfortable with kind of the setup here, the context to it. But beyond that, hopefully nothing here is too tricky.